Before describing the essence of our propositions, it wouldn't be inappropriate to recall some matters of common cryobiological knowledge. Any means of cryopreservation generally relies upon vitrification, in which cells survive in glass between ice crystals. Even under slow programmable freezing, cells are surrounded by unfrozen liquid between growing ice crystals. Vitrification is a process whereby fluid becomes a solid during cooling. More precisely, exhibits most of the properties of solids, without any substantial change in molecular arrangement or thermodynamic state variables. Hence, no crystallization with a consequent heat release and volume increase. Proposals of simultaneous vitrification of entire samples without the formation of ice even predate the discovery of the first cryoprotectants in 1940s. However, the first practical implementation of vitrification with murine pre-implantation embryos was carried out only in 1985 by Gregory Fay and William Rowell. The main condition for the onset of vitrification during cooling is an increase of liquid viscosity after about 10 to the 13th Poisson. On the molecular level, it is expressed in loss of rotational and translational degrees of freedom, leaving only bone vibration within a fixed molecular structure, which leads to a decrease in the specific heat and thermal expansion coefficient. Cryoprotectants lower the critical cooling rate, which is not less than 10 to the 7th degrees per minute for pure water, required for vitrification, inversely proportional to their concentration within the cooling solution, reducing it up to quite available speeds. Cryopreservation of individual cell suspensions requires nothing more than a slow programmable freezing, and the vitrification protocols for whimsical pre-implantation embryos are even more easy to apply. However, when dealing with macroscopic objects, researchers are faced with a number of additional obstacles, namely, 1. The toxicity or extremely high cryoprotectant concentration, up to 60%, required for vitrification. 2. Uneven cryoprotectant distribution in organ parenchyma. 3. Irregularity of cooling with temperature gradients. 4. Insufficient cooling rate. 5. Cracking during storage below glass transition temperature. 6. Occurrence of nucleation sites at about glass transition temperature. 7. Insufficiently slow and uneven warming with temperature gradients and local overheating. 8. Devitrification during warming due to insufficient heating rate with ice recrystallization. 9. Reperfusion syndrome at the end of the rewarming. Ice formation during warming happens faster than during cooling because ice nucleation occurs at lower temperatures than ice growth. This nucleation leads to extensive ice growth at warmer temperatures. That's why the so-called critical warming rates are typically 2 or more orders of magnitude greater than critical cooling rates. The same stringent and even contradictory conditions are imposed on storage temperature and transport of macroscopic samples, because masses of vitrifiable tissues larger than a few cubic centimeters almost invariably develop large-scale fractures. Storing them at liquid nitrogen temperature leads to cracking due to shear stress relaxation, while keeping them close to the glass transition temperature, down to 15 degrees, results in the formation of nanoscale ice crystals due to lateral diffusion of water molecules, which increases the critical warming rate upon subsequent heating. A detailed review of the entire spectrum of research requires a separate report and goes beyond the scope of our work. The more so because no major success has been achieved yet, excluding successful vitrification of blood vessels, peripheral nerves, pancreatic islets, and so on. Although speaking of nerves and blood vessels, I personally believe it is rather a tissue engineer in the cryobiology. The most promising advances in this field were made by the company of 21st Century Medicine, a company led by Gregory Fay and Brian Walk. In 2005, they have reported on a rabbit kidney that survived vitrification and subsequent transplantation with immediate contralateral nephrectomy, successfully functioning for 9 days. However, due to the above-mentioned unresolved problems, this experiment remains anecdotal so far. We know three possible ways of macroscopic biological object accelerated warming: the dielectric warming, vascular perfusion with inert fluids that remain liquid at cryogenic temperatures, and gas perfusion. Dielectric warming results in very uneven heating. Cooling solutions to cryogenic temperatures directly by cryoprotectants is impossible due to progradient solute viscosity and peripheral vascular resistance elevation. As a result, the perfusion rate decreases. From a certain moment, instead of passing through the microvasculature, refrigerants begin to shunt through the major vascular arcades. Respectively, the heat exchange is complementarily weakened, and cooling becomes irregular. With a further increase, viscosity perfusion either stops or ruptures in the parenchyma occur. Liquid perfluorocarbon-based coolants proposed by Michael Darwin and Brian Walk are partly able to solve this problem, but as I have said, only partially for the same reasons, albeit at lower temperatures. Gaseous coolants, despite their negligible heat capacity, have 2 to 3 orders of magnitude lower viscosity and freely pass through the vascular bed even at cryogenic temperatures. The most popular in this area is helium, due to its low condensing temperature and the highest diffusion mobility. Of course, the gas perfusion has its own shortcomings. Low heat capacity forces the use of high pressure to increase the heat transfer, which is fraught with barotrauma. Gas embolism, particularly during rewarming when the gaseous coolant is replaced by a liquid. Drying up of endothelium and the adjacent tissue areas. In view of the foregoing, for vitrification of isolated organs suitable for transplantation after storage and rewarming, and eventually up to intact organisms, we plan the following. 1. Application of combined use of traditional cryoprotectants with clathrate forming gases as a means for vitrification. We turned our attention to xenon because of its absolute non-toxicity on tissue and cellular level, while even the most low-toxic cryoprotectants such as glycerol, ethylene glycol, etc., are potentially dangerous due to osmotic effects. In order to evaluate the cryoprotective potential of xenon, we have conducted 2 series of experiments with Baker's yeast and mammalian cell cultures in custom-built bronze miniature hyperbaric chambers, which you can see on the picture. Yeast survival at all xenon pressures tested from 3 to 7 bar after 2 hours of pressure chamber exposure at minus 20 degrees with subsequent chamber immersion in liquid nitrogen, 68.5 plus or minus 6%, turned out to be better than in control, 35 plus or minus 6%, and comparable or even higher to that of 5% glycerol application, 50 plus or minus 25%. Joint application of xenon and glycerol showed 71 plus or minus 15% of cell survival. However, the experiments with mammalian cells at xenon partial pressures from 2.5 to 12 bar upon slow programmable freezing showed complete cells destruction upon conventional rewarming. Even after designing a sophisticated decompression protocol, we could not achieve survival upon thawing, opposed to a joint application of xenon plus 5% of dimethyl sulfoxide that usually showed more than 80% of survival. This made us disappointedly conclude that xenon has no cryoprotective properties applying slow programmable freezing. Well, unexpectedly, 2.8 plus or minus 2.3% of control cells group frozen by the above-mentioned primitive yeast protocol survived. And moreover, fastest achievable cooling speed of direct placing of pressurized hyperbaric chamber into liquid nitrogen, which we considered an absolute death sentence in the other control experiment, improved cell survival up to 22.5 plus or minus 13.4%. Large-scale molecular dynamics simulations of xenon clathrate hydrate, and nice crystal growth, recently described in our report, possible mechanisms of cryoprotective effect of xenon, indicate vitrification of water inside cells, especially under combined application of xenon and dimethyl sulfoxide, as a possible explanation of these results. The main thing for us is that the hydrophobic solubility of xenon in low temperature water increases with cooling faster than the thermal stability of clathrate hydrate. As a result, it should turn out that traditional cryoprotectants, by suppressing xenon crystalline hydrate formation on cooling stage, would allow the solution to be saturated by xenon to a significant increase of liquid viscosity, which is enough for vitrification. So this would enable vitrification using a much lesser amount of chemical cryoprotectants, and thus yield large decrease in toxicity. We have submitted a patent application. It sounds so simple, even primitive, that I first could not believe that anybody think of this before. The second critical step is to develop a methodology for a fundamentally new approach to a uniform heating of complex biological objects by means of electric and magnetic fields phase emitters guided by MRI thermometry, which will be described in details in our next report. 3, creation of an improved carrier solution for cryoprotectants with an emphasis on organ conditioning, prevention of chilling injury, neutralization of reactive oxygen species, activation of apoptosis cascades, and overall reperfusion syndrome during rewarming. 4, slight improvement of gas perfusion methodology. Increasing the heat exchange efficiency should be achieved through a conjunction of elevated persiflation pressure with modulation of sonic and ultrasonic waves. 5, application of frequency and width pulse electromagnetic field modulation within the initial stages of cooling, not confining to a simple 50 Hz oscillation used in cells alive system, low temperature freezer of Abico Corporation. 6, determination of the best storage temperature for objects vitrified by our method, taking into account the alleged stabilizing effect of gas cryoprotectants. Unfortunately, we cannot do all of the above since we run out of money, so this is all a mere theory. Well, I personally ran out of funding opportunities in Russia because it seems that nobody is interested in it. Well, as Igor Valentinovich has already said, we're open to any type of collaboration. Well, thank you for your attention.
Why are you trying to activate apoptosis cascades?
I meant prevention of apoptosis cascade activation.
Could you review a little bit what was the benefit? Did you get any benefit of xenon compared to the traditional cryopreservation? Was there any benefit in any laboratory setting for mammalian cells?
Well, you see, one of the control groups, which was cooled with the maximum possible speed, well, showed elevated survival, well, up to 40% in one of the series of experiments. I mean, 22.5 plus or minus 13.4%.
And without the xenon, it was 2%, if I remember rightly.
No, without xenon under the same speed of cooling, they were 0%. And when we tried to freeze cells with the primitive yeast protocol of 2 hours of cooling, at minus 20 Celsius with subsequent immersion in liquid nitrogen. Well, there are almost 3%, 2.8 plus or minus 2.3% of cells turned out to be alive, though we said there should be none.
Why do you call the Fahey-Wolf experiment anecdotal?
Well, nobody, including themselves, could not repeat it later, up to the present moment.
They've tried to repeat it.
Yes.
That's not been published, though.
Yes, actually, they tried almost 300 times, and just one.
300 times?
Yes. No, well, maybe more than 300 times.
Clarify a bit about this. So I talked to Greg about this fairly recently, and a lot of the reasons why it was difficult to repeat was because of the there was an important reagent that stopped being manufactured, and they couldn't replace it, and they ended up having to essentially rebuild the entire protocol in a lot of different ways. I believe that Greg's latest data is that they're getting close to being able to repeat it, but they were basically prevented from doing the obvious repetition because of unavailability of an important reagent.
Thank you. It's certainly one of the most important experiments in our movement, the Fahey-Wolf experiment.
I'm not a physicist, so sorry if this is completely naive. But as far as I remember, pressure is important to how gases behave. So on your last point, the storage conditions of whatever you've cryopreserved probably have some bearing, or will the tissue behave differently if it's been cryopreserved with xenon, depending on the storage conditions and the pressures therein?
Well, when being frozen, the xenon clad hydrates are quite stable, so there's no need in any special barrow chambers, etc. So though it is quite difficult to thaw them because of the decompression procedure, it should be, well, rather sophisticated.
I'll get back to you after.